This is the first.
Hello, sir. Our problem is permutation matrix column subset selection. So, in machine learning, while handling high dimensional data, we often do dimensionality reduction. For example, one of the techniques is SVD, where we minimize the Frobenius norm of the error with the low rank approximation of the matrix. Alternative way to do the dimensionality reduction is the column subset selection, where you select a subset of the entire data set and reducing the dimension. So the applications of the column subset selection are, one is dimensionality reduction, and we can also select the important features from the given data set. Also the compression, it can also be used for compression of data. So to formally state our problem statement is given a matrix of size n cross d and an integer which is much smaller than d. We want to select the k columns from the matrix A such that the residual error from the reconstruction is minimized. So for the problem, we have prepared two papers that we have studied. First one is learning latent permutations with Gumbel Synchron networks. So many problems in machine learning involve learning the permutation for sorting, ranking, matching problems. In our example, we want to rank the columns in order of their relevance so that the reconstruction error is minimized. So, but the problem with selecting these permutation matrices, they are discrete. So, for an n cross n permutation matrix, the set of all n cross n matrix contains n factorial elements. So, sampling from that set is very difficult and it's not differentiable. So, for that, the authors of this paper have proposed Gumbel Synchron networks, which provides a differentiable approximation for the sampling operation. So for some basics, permutation matrix are binary matrix where each row sum to 1 and each column also sum to 1. And but the permutation matrix are, as I said, are discrete. So we use a relaxed version of permutation matrix, which is Markov-Politov. It is a convex combination of all the n cross n permutation matrices, and all the doubly stochastic matrices come inside this Politov. So generally, when we sample from a categorical distributions, it is a random process and it is not differentiable. So we use Gumbel max trick, which is we add a Gumbel noise to the log probabilities of each category. So this converts the sampling operation into an optimization problem. So sampling from the categorical distribution is equivalent to solving this optimization problem. So this is also acts as a reparameterization trick. So the randomness in the sampling operation is separated into G, which is an independent parameter, and the rest of the probabilities, which are all model parameters, they are in a separate variable called pi. So this allows for the gradient flow because we can differentiate with respect to pi and not worry about the randomness in G. So, but still this optimization problem contains argmax, which is not differentiable. So for that we use softmax relaxation, which analogous to category classification, where we get the logics and we use softmax to get continuous approximation. So here we use a temperature parameter tau. As tau gets close to 0, it approximates the discrete one-hot encoding. So the output that we get, so we want our matrix to be doubly stochastic. So we use Synchron normalization. This is an iterative process. It alternatively normalizes rows and columns. But the actual Synchron normalization is a limit to infinity. But in practice, we use a limit on number of steps that we perform. So overall, the Gumbel-Synchron algorithm is given a score matrix, which is essentially probability matrix. We first sample it using the Gumbel max trick and normalize using the synchron operator. Since the both steps are completely differentiable, this allows for the uh, this optimization using gradient based algorithms. So the scoring matrix, we can use neural networks to get our scoring matrix. Then we get the permutation matrix from the Gumbel synchron algorithm.
You're not getting permutation matrices, yeah, you're getting doubly stochastic matrices, right?
Yeah,
You're
we're getting
the convex hull,
yes.
and then you'll do relaxation. Is that what it is?
Yeah, we the
I mean, you'll use a relax.
we
After
get a,
the Gumbel synchron
yeah
step, you will discretize.
yeah we get the relaxed version of the permutation matrix.
Which will discretize.
While inferencing, we can discretize the.
So gradient flow is for learning the
We
network that produces the score matrices.
yes. For relevance to our problem, the column subset selection can also be modeled as a permutation matrix learning, where AP transpose arranges the columns, and IK we can get the top k columns, and P again arranges back, and we can minimize the reconstruction error in this. This is overall architecture. Given an input matrix A, our neural network gets a score matrix S. Then we use Gumbel Synchron to get a software version of permutation matrix. So for feature selection, we can use uh, problem-specific contextual information, and we can also use SVD-based features or the leverages score from diagonal matrix. Also the pairwise correlation between the, these are all the different methods by which we can get the scoring matrix. So for the getting the scoring matrix, we can use different kind of information. So either this one correlation between.
I thought you only said that using a neural network to get your S, right? S is your scoring matrix.
S is the scoring matrix. For neural network, we can use multiple informations, right?
So you're saying those are features that affect the neural network.
Yeah, those are the different features we can be used to give the neural networks as an input.
This column norm, what are those? Column norm, leverage scores diagonals of pairwise correlations between columns, spectral information, problems with contextual information. Okay.
So the advantages of Gumbel Synchron are it's completely differentiable. We can introduce many different metrics for the calculation of our scoring matrix, and it can easily generalize to any problem that involves a computation of a permutation matrix. It's a general algorithm. So the Synchron normalization algorithm is given like this. So it iteratively normalizes the first row, then column, and it iterates over multiple steps. So the training implementation is we get the scoring matrices from the our model neural network. Then we use Gumbel noise to get a sample. Then we normalize it using Synchron normalization. We can compute the loss between the reconstruction.
So one question, is there any regularization at all here?
So,
Was there any regularization?
so the Gumbel Synchron is just an algorithm to sample the software version of permutation matrix.
Yeah, but you're still doing backpropagation through the network,
Yeah,
right?
that we can add the any regularization and loss
Is there
function.
any specific regularizer that is consistent with doubly stochastic? I mean, the convex hull itself or the original
So the depends on the problem context. So for different problems, they have used different regularization metrics have found to be more effective.
What examples they have used in a
So
regularization?
the authors have tried on sorting the numbers.
Hmm.
And
So for sorting, what
MNIST,
regularizer did they use?
I think it was L1, and another one was this thing. MNIST data set. The images were
And there, what
sorted.
regularizers did they?
They use L2.
Sorry.
L2.
Yeah. So this is the second paper that we went through. This is the linear time approximation algorithm for column subset selection. This uses local set. Uh, yeah. So like first, the paper actually begins with comparing different methods along with their algorithm, and like what they propose in this paper is a novel approach in which they keep the running time to be proportional to the dimensions of the matrix. So n is the number of rows and d is the number of columns in the matrix, and k is the like subset of columns that you are selecting. So like the previous algorithms that were proposed, some of them, as you can see, are linear in terms of dimensions of the matrix ND, like the adaptive sampling technique, for example. But however, they had a very bad error approximation ratio, which was in terms of a factorial. So what they propose is a method that keeps the running time in order of the dimensions of the matrix, and also reduce the approximation ratio, like error approximation ratio, to be of a linear time algorithm. So yeah, so like they have used two algorithms here, which they have proposed. So like one is a local search column selection algorithm, and uh, this is the second algorithm. Like this is the core foundation of our project proposal. So like we'll go through the algorithm in detail in the next slide. Yeah. So the algorithm basically like begins with initializing the empty set of column indices, and we set the error matrix to be the complete matrix because we haven't chosen any columns in the beginning, and we are just storing the original matrix to be used for later use. Uh, yeah. Then what we do is for each of the like.
Can you go back to the previous slide once more?
Yeah.
Sorry. So you're basically empty set indices are you start with a very small in low damage. Uh, so this matrix is not guaranteed to be square here, right?
Uh,
Matrix is not guaranteed to be square. You're saying set empty set.
yes, yes. The matrix is not guaranteed to be a square matrix. Yeah. So yeah, so from each of the k slots, we sample a column proportional to the residual norm. The basic intuition behind it is that a column with a larger residual norm will have a larger variance. So we are trying to use a greedy approach to like include it in our like subset selection, so that like the error of reconstruction will be minimized. So yeah, so the residual error is composed in the following way. Like here, this is the Moore-Penrose inverse of a matrix. So this handles the fact that the matrix is not a square matrix, and yeah, so we are just basically like sampling the column with the probability distribution proportional to the residual norm of the column. Yeah, and also in the first iteration, yeah.
I mean, this is like OMP, isn't it? Like OMP.
No.
It won't, but the algorithm looks like an OMP. Orthogonal matching procedure. So,
Yeah.
but is there orthogonality here?
No, no, orthogonality is not enforced here.
So every index that you collect, should just reduce the error. There's no
Yeah,
orthogonality.
no orthogonality enforced here. Uh,
There must be some constraint on the indices. No? I mean, see, the problem is, so can you go back to the line which selects the column index, next column?
Yeah.
probability column I is selected. This column I is from
From the original matrix.
right.
So we basically like you have a matrix and you say that you need k columns from that matrix. So you are just sampling k columns and then computing the reconstruction error. And we like put this so that we match the dimensions for the error, the inverse and the yeah. And also in the first iteration, like we have added a diagonal matrix has been added in the paper to enforce perturbations in the original matrix. This ensures that the like optimization does not stuck in a get stuck in a local minima, and they have like proposed this to be the diagonal matrix which work for them, and yeah. So this also diversifies the selection of the column. Yeah. So then finally, like we compute the matrix as B was the original matrix that we had started with, and D is the perturbation that we added in the matrix. And then we like just take the columns as per our column subset selection.
Sorry, what is first phase and second phase? I missed that. You said column selected in second phase. I didn't even realize there was a phase 1 and phase 2. What are the, you said second phase. So I missed. Are there two phases?
First iteration, you're just like creating adding a perturbation in the original matrix, and you aren't selecting anything. Then after that, you keep on selecting a column and
Second phase
minimizing
is the actual.
yeah.
Also, I mean that.
Yes.
Okay, second phase is the phase we are talking about.
Yeah. Yeah. So like once we get the matrices, now what we are doing is we are applying a second algorithm called the local search algorithm, which basically looks in the local regions of the matrix and tries to see if we can improve on the column selected. So yeah. So for this yeah. For this, we first like compute again the residual error, and we like sample again based on the residual norms. We take around 10K elements. Then next one. Yeah. So we sample around 10K column indices with the probability proportional to the residual norm. And then what we do is we keep on swapping them with the elements which we have already selected and check whether it improves the error or not. So this is what they've proposed, and they've given some theoretical guarantees for the convergence. So
basically, it is. I mean, it's almost like a genetic algorithm, right? So it's just
yeah, so it's like first you select certain
and
then you keep on swapping and checking whether it improves or not.
So swapping means swapping with one not selected.
Yeah. So like you randomly take one index from your originally selected columns, and then you take around 10K indices, and then you just keep on.
But is it guaranteed to give any convergence? Just like it sounds like the genetic algorithm, right?
Yeah. But then they've given theoretical guarantees in the paper for it.
What are the
Like like stated a lot of lemmas and showed that that this will converge with a k plus like in a linear error rate, basically approximation of the error, and the order of convergence.
Do you have any slide on the? You're talking about the guarantees. Okay.
Uh, so this like also preserves the approximation quality because we are essentially using the entire original matrix without taking a lot of approximation, except the thing that we had just perturbed it in the beginning slightly. And yeah, so like this factor is chosen just to balance efficiency and quality. Otherwise, like choosing a larger subset actually takes more time. So they have come up with this number, 10K. So like this is the number of indices you are using for swapping, candidate indices for swapping. So you pick one from the original set and then you swap it with these number of columns which are present in the yeah 10K. Yes. So if K is 5, so you will swap it with around 50 different columns with the residual error proportional to the distribution. K is the number of columns that you want to select. So you are essentially, instead of using the entire D number of columns, you are just swapping with 10K columns and checking whether it's better or not.
But assumption here is K, I mean,
K is very less
K is very less. So that
as
technically
compared to N and D.
is smaller than D.
Yeah, very small as compared to D.
Itself should be small.
Yeah.
Okay, under that it will be K plus 1 guarantee.
Yeah. So like these were the key innovations in the paper, like the matrix perturbation to avoid the local optima condition, and they have used a two-step mixed sampling strategy. One is first sampling proportional to the residual norms, and then like uniform sampling from the candidates, which is basically the swapping strategy. And this is done iteratively to improve the quality. And they have the theoretical guarantees that they have given is the approximation ratio for the error is around linear, and the time complexity like for running of the algorithm is proportional to nd, the dimensions of the matrix A.
So this
And it has been like
approximation ratio doesn't sound to be great at all. No? Very
we'll go back to the first one, because like compared to all the previous other paper, like this was the best approximation ratio that they had got. And yeah, like this is linear in time. Others were k square log. Like this was order k square. That was factorial. So, and the ones which were linear, they basically were not good in terms of running time, because n is very large as compared to k. Yeah. Uh, yeah. So coming to our project proposal. So what we noticed in the previous algorithms, there were a lot of discrete steps. Like we had sampled and all. So this makes it very difficult for you to use a neural network to learn this entire process. So for neural network, we would either want it like we would at least want it to be continuous. So what we are proposing is a method to to make continuous approximations of the discrete steps and train a neural network on the entire linear column subset selection algorithm, and see if we can improve the the bounds for the error approximation ratio and the running time as well. So yeah, this is summary of the key discrete operations in the algorithm that I showed you before. One is the discrete sampling, that we sample the columns based on the residual norms. And then we also had some set operations in which we had added column indices to a particular set and removed them. And there is also a binary membership test that we check if a column belongs to a particular set or not. And finally, the objective is a discrete minimization problem. So
so
basically,
basically you're taking uh, the foundational inspiration from the paper you presented,
Yeah.
LSCSS,
yeah,
and the inspiration of the
Gumbel.
relaxation kind of thing from
Yeah, yeah. And the Gumbel paper, like which he had
Gumbel.
presented, that will give us one basic idea of relaxation at a particular point. So that will be used to continuously approximate this, and we can train a neural network on it.
Okay, that's interesting. Very, very different.
Yeah, we are doing slides.
Yeah.
Yeah. So like these were
And this
the discrete
can also have some implications in tensor parallelism itself, because the tensor parallelism itself is a lossy and approximate thing, right? You can find a permutation. Okay.
Yeah, so these are the discrete operations that were there, and these are the continuous approximation steps that we are trying out. So like first one was a sampling of column indices, which was discrete, and then we are using the Gumbel softmax idea for the differentiable sampling, and then adding and emptying the set, like we are using soft membership values, and like we are using a differentiable reset gate for value reduction. And for creating the zero matrix, even that was again a problem. Like it's a discrete step. So we used weighted matrix operation using the membership scores which we had stated before. This. Again. Yeah, so these were in the first algorithm, and now this is the swapping algorithm basically. It also has a certain set of discrete operations. So selection of column indices again, and uniform sampling from the selected indices. So we have again used a soft approximation for that. And using set membership testing, we have used a continuous membership function using the sigmoid function. And to find the index minimizing objective, we have used a soft argument instead of the hard uh, objective function. And by adding or removing elements to the set, we have used continuous weights for set weight. Uh, yeah. So our idea is to use a neural network module implementing these algorithms. We have already implemented it and we have tried it on a subset of data. So like we would like to share a bit of our results as well. So yeah, so this is the architecture that we used. So we used a continuous column selection module, which we defined using the paper, and then we used a downstream classifier network to check whether the reconstructed matrix does it give us give us similar results as compared to the original matrix, like on classification tasks. So so yeah, our data set was MNIST, and we only used a subset of the MNIST. We used 10,000 samples from the MNIST data set, 80 for training and 20% for testing.
What is the problem
Yeah, so
which you're trying to solve for MNIST?
yeah,
Where
for MNIST,
implementation becomes important.
yeah, we are trying a feature selection for MNIST. So what we are doing is for the entire image, 28 cross 28 image, we are flattening it into a single vector and seeing which pixels are of importance for us to classify it well. So from that 784 cross 1 vector, we are choosing k number of pixels only, and each k will be same for every example, and seeing whether that small subset of data can help us to get similar classification results as compared to the entire 784 pixels. So yeah, these are a few of the things that we use. Like the optimizer, we used Adam optimizer, and we used the reduce LR on plateau scheduler with a patient of 3 and a factor of 0.5. And our batch size was 128. We only trained it for 10 epochs, and yeah, like 10 for the column selection and 10 for the classification task. And yeah, we also used temperature annealing. Yeah. So these were the results that we got. So 784 is the entire data set, and on the entire data set we got a classification accuracy of around 93.5%. With the same neural network, when we used only 5 features with our continuous approximation, we got an accuracy of around 43%. But as you keep on increasing the number of features, the number of pixels that you are choosing, the accuracy seemed to increase, and for around 50 features we are getting around 88% of accuracy. And so uh, like so these are the results for the image that we chose. So like for k equals to 50, these were the image pixels that were chosen, and you can see that all of them are same in all the images. And these were the selected pixels. That was the mask, and these are the selected pixels. And you can easily see that it is essentially capturing most of the important information in the image. Like for example, the numbers can be almost made out from these 50 pixels itself. So that is the reason we got around 88% of accuracy. Yeah. So
Very
these are the
interesting.
things that we plan to do further. One is ablation studies using the temperature parameter that we had used as a.
But it's still not clear. I mean, it's great work, but it's
Yeah.
not clear what is. I mean, have you baseline against LCL or whatever that the other two approaches? Baseline. What are your baselines?
Oh, okay. Sir, the baselines that have been given in the paper, actually, they had mentioned a site for the data set, but there is a bad gateway on it, so we aren't able to find those data sets. So what we did is we used this as the baseline, like the entire 784 pixels, and we used its classification as the baseline for.
So your current evaluation is only based on your approach.
Yeah.
Not been. I mean, just fine.
Yeah.
A project. and by your project presentation time, it will be good to have
Yeah.
some baseline.
So
I mean, sometimes random is hard to beat also. So
like in the paper, they have given only the time for like the time and the memory use. So they haven't reported like classification results. Yeah. Yeah, yeah. Yeah, we are planning to do that. Like, written it. Yeah. So like one part is to like change the temperature parameter. We haven't played with that a lot, and also like exclude the perturbation step and see what the results come out to be. And since we have like kept the number of iterations to be only around 10, we hope that probably increasing the number of epochs might help us to converge to a better result. And also we haven't changed the dimensions of A, which is essential for us to uh, like tell about a running time with respect to the dimensions of A. So this is what we plan to do. And with the comparative studies, we were trying to like compare it with PCA and SVD based approaches for feature selection. And also the other differentiable feature selection methods which have been mentioned in the paper. They have only given the time and the memory of that for now. And the comparison metrics are the accuracy versus feature count. Yeah. Okay. And time and memory. Yeah. So like this is just the basic questions that we would want to answer with this project. Is that like how close is it as compared to the discrete algorithm? Is it better than that, and can we derive? Yeah. It won't be theoretical. It will probably need to do a practical theoretical bound, like plot K versus uh, yeah. Yeah.
even under some assumptions, like limited setting, you're not doing. See, ideally, we very large data sets.
Mhm.
You can become between illness and
Sir,
gain algorithms
Mhm.
and or
they have taken.
presentation.
So I think one the next one is I think the enormous amount that's after being
Yeah, that will take.
but this is connected to the this one. So they
That's
won't
okay.
present on the slides maybe.
Stay back. You should stay back for their present.
Yeah.
You are present. So I think
Sorry?
it's a continuation of this.
Yeah. So how do we good work? We should try and push it to users. Good work. But I think other scale and experiment are necessary. Slice GPT might be the slice GPT, right? Good.